6 square plus 8 square, so it is 36 plus 64. So your answer is 0.06 plus j 0.08. Again it is in rectangular form, convert it into polar, so it is 0.1 angle 53.13, unit is mho. Now we have to find the total supply voltage. So for that you have to find the equivalent value of the admittance Y equivalent, which is equal to Y1 plus Y2. Y1 and Y2 is already known, so it is 0.03 minus j 0.046 plus 0.06 plus j 0.08. So it is equal to 0.09 minus j 0.126. Again convert it into polar form. So your answer is 0.15 angle 56.46. So Y equivalent is known to us. Now supply voltage V is equal to I into Z. Now instead of impedance we are consider here effect of admittance. So Z is equal to 1 upon Y. So our equation is V is equal to I upon Y equivalent, because Z is equal to 1 upon Y. And the value of Y equivalent is known. We are already found the value of Y equivalent, which is 0.15 angle 54.46. So put the value in this equation, you can find the value of supply voltage. So it is magnitude of current is given, it is 20 ampere. So here it is 20 divided by 0.15 angle 54.46. Simplify this equation. So your answer is 133.3 angle 54.46 volt. This is your answer for a supply voltage. Okay. So whenever parallel circuit is given to you, instead of impedance you have to consider the effect of admittance. So first of all find the admittance for an individual branch, then find the equivalent admittance, and then find the supply voltage. Now second example is one resistance of 10 ohm and inductance of 0.2 Henry and capacitor of 100 microfarad are connected in series across 220 volt 50 hertz supply. Determine impedance, current, voltage across R, L and C and the power factor. So the data given to you is resistance is given, which is 10 ohm, inductor is given, it is 0.2 Henry, capacitor is 100 microfarad and XL is equal to 2 pi FL. XL is the inductive reactance, which is equal to 2 pi FL. Frequency is given, L is given, so you can find the value of XL. So it is equal to 2 into 3.14 into 50 into 0.2. L is our 0.2 Henry. So your answer for inductive reactance is 62.8 and unit is ohm. So this is the value of inductive reactance. You have to find the value of impedance. So now you have to find the value of capacitive reactance also. So the equation of capacitive reactance XC is equal to 1 upon 2 pi FC. Again value of frequency is known to you, value of C is also given. So our equation is like this, it is 1 upon 2 into 3.14 into 50 into 100 microfarad. So it is 100 into 10 raised to minus 6. So our answer for a capacitive reactance is 31.84 ohm. Now you have to find the value of impedance. Impedance Z is equal to R plus JX, and X is the combination of XL and XC. Now in this particular example, XL is greater than XC. So it will indicate it is inductive circuit. So equation of Z is under root of R square plus XL minus XC whole square. If XC is greater than XL, then it is XC minus XL whole square. As it is inductive circuit, XL is greater than XC, so your equation is XL minus XC whole square. Put the values, so it is equal to under root of 10 square plus 62.8 minus 31.84 whole square. So your final answer for impedance is 32.57 ohm. Now equation of current I is equal to V divided by Z. Value of Z is already found. Value of voltage V is given, it is 220 volt. So put the value of voltage and impedance, so you can find the value of current. So it is like this, it is 220 divided by 32.57, it is our impedance. So your answer for a current is 6.75 ampere. Now you have to find the voltage across resistance, which is denoted by VR, and it is equal to I into R. Now the value of current is 6.75 and it is a series circuit, so the current passing through the R, L and C is same. So I is equal to 6.75 into value of resistance, which is 10. So it is 6.75 into 10. So your answer is 67.5 volt. Now voltage across inductor VL, which is equal to I into XL. I is equal to 6.75 and value of XL is 62.8. So your final answer is 424.19 volt. Now voltage across capacitor VC, which is equal to I into XC. Value of XC is already found, which is 31.84. So your VC is equal to 6.75 into 31.84 is equal to 214.92 volt. Now power factor. Power factor is denoted by cos phi, which is equal to R by Z. R is the resistance of the circuit and Z is the impedance of the circuit. So value of R is given, it is 10 ohm, and value of impedance is already found, which is 32.57. So your answer is 0.3. And as we are discussed earlier that it is an inductive circuit, so your power factor is always in a lagging mode. If it is capacitive circuit, then you have to specify here it is lead. So whenever the value of inductor and capacitor is given, first of all decide that it is inductive circuit or capacitive circuit. Accordingly specify in the power factor lagging or leading. It is compulsory to specify the mode of power factor, lagging mode or leading mode. Okay. Now next example. A circuit consists of a resistance of 4 ohm and inductance of 1 Henry, and a variable capacitance is connected in series across a 100 volt 50 Hz supply, and you have to calculate the value of capacitance to produce resonance and the voltage across capacitor. So one circuit is given, it is a series circuit, resistance and inductor, value of resistor and inductor is given, and one variable capacitor is connected to this particular circuit, and you have to find the value of capacitor which is produced resonance in the given circuit. As we know, in series resonance circuit, when XL is equal to XC, it is the condition at which your resonance will occur. So you have to find the value of capacitor in such a way that it is exactly equal to the value of inductive reactance. So for that, first of all you have to find the amount of current passing through the given circuit. So I is equal to V divided by R. Value of voltage is given, which is 100 volt, and resistance is 4 ohm. So I is equal to 25 ampere. Now inductive reactance, value of L is given, frequency is given. So XL is equal to 2 pi FL. So it is 2 into 3.14 into frequency is 50 Hertz and inductor is 1 Henry. So it is 50 into 1 and your answer is 314 ohm. So this is your inductive reactance. Now you have to find the value of Xc in such a way that XL is exactly equal to Xc. So it will indicate the resonance circuit. So at series resonance, as we know, XL is exactly equal to Xc. So inductive reactance is equal to capacitive reactance. Hence Xc is equal to 314 ohm, because we are calculated value of XL is equal to 314. So Xc must be equal to 314. So Xc is equal to 1 upon 2 pi Fc. So you are compare these two values and you can find the value of capacitance C, which is equal to 1 upon 2 into 3.14 into 50 into Xc, which is 314. So your answer for a capacitor is 0.1 microfarad. So this is the value of capacitor which produced resonance in the given circuit for a value of inductor which is equal to 1 Henry. If you are change the value of inductor, obviously the value of capacitor will change. Now voltage across capacitor, again Vc, which is equal to I into Xc. So it is equal to 25 into 314. So your answer is 7850 volt. This is the voltage across capacitor at the time of resonance. So whenever example based on a resonance circuit is given to you, always keep in mind that at the time of resonance your inductive reactance is exactly equal to the capacitive reactance. So if certain data is not given, you have to use this equation and find the remaining values. Now next example. This example is for a three-phase circuit. So a balanced star connected load of 4 plus J3 ohm per phase is connected to a balanced 3-phase 400 volt supply. Find the line current, power factor, active power and reactive power for a given circuit. So you have to find the line current, power factor, active and reactive power. So first of all you have to find the impedance per phase, which is denoted by ZPH and which is equal to 4 plus J3. 4 plus J3 is given. It is given that star connected load. So obviously load is always in terms of impedance. So it is your impedance per phase. So it is 4 plus J3. Convert it into polar form. So find the magnitude and phase angle for this particular equation. So your polar form is 5 angle 36.86. Now load is star connected. As we know, whenever any circuit is connected in star, then the current passing through this circuit means line current is exactly equal to the phase current. But if you are finding the voltage, then line voltage is equal to root 3 of phase voltage. So you have to use this relation for this particular star connected load. So your line voltage VL is equal to root 3 VPH, which is your phase voltage. So your V phase means phase voltage is equal to VL by root 3. And the value of line voltage is given, it is 400 volt. So your phase voltage is equal to 400 divided by root 3. So your answer is 230.9 volt. This is your phase voltage for a given star connected load. Now you have to find the phase current for this particular star connected load. Phase voltage is already known. Now we are finding the phase current for this particular load connection. So the current per phase I phase is equal to V phase divided by Z phase. So V phase is 230.9 and Z phase is 5. So your I phase is equal to 46.18. So your phase current for a given star connected load is 46.18 ampere. Now it is a star connected load. So line current and phase current both are same. So IL is equal to I phase, which is equal to 46.18 ampere. Now power factor for this particular load is again same equation, R by Z, but it is a three-phase circuit, so you have to consider the phase values. So it is R phase divided by Z phase. So R phase is 4 and Z phase is equal to 5. So it is 4 divided by 5. So our power factor is 0.8. Now power factor is known to you. Now using the value of power factor, you can easily find the value of real power as well as reactive power. So equations are also known to you. For real power, equation is VI cos phi, and for reactive power it is VI sin phi. Cos phi is already found. So this is the equation for real power, P, which is equal to root 3 into VL IL cos phi. If it is three-phase circuit, you have to consider the values of line currents and line voltage. If it is a single phase circuit, so it is just VI cos phi. So this is the basic difference between single phase and three-phase circuit. In single phase, real power is equal to VI cos phi. In three phase, it is root 3 VL IL cos phi. So again, VL and IL is known, cos phi is already found. So P is equal to root 3 into 400 into 46.18 into 0.8. So it will give you the value of real power in terms of watt, which is equal to 25595.5 watt. 25,595.5 watt is the real power for a given circuit. Now reactive power, which is denoted by Q and which is equal to root 3 VL IL sin phi. So again it is root 3 into 400 into 46.18 into 0.6. So our answer is 19196.6. This is the reactive power for a given circuit. So whenever three-phase circuit is given to you, first of all identify the connection. If it is star connection, then the current passing through this particular circuit means line current and phase current both are same. If it is delta connected, then the voltage for this particular circuit means VL and V phase both are same. So first of all identify the connection, then use the relationship for voltage and current for a given connection, and then find the equivalent circuit and then find the parameters that which is found by a given circuit. Suppose you have to find a power, then for a single phase it is VI cos phi, for a three phase it is root 3 VI cos phi, and V and I are the line values, not a phase values. So always remember, whenever